Welcome to Unit 7 on factoring. Factoring is one of the most important skills that you can take with you to Math 2. In this lesson, we want to talk about factoring by GCF, which means greatest common factor, and factoring by difference of squares. A little bit of background. Factoring means to rewrite a polynomial as a multiplication problem instead of as an addition or subtraction problem. So for example, we want to take something like 6x plus 12 and rewrite it so that instead of an addition problem, we have a multiplication problem. So 6x plus 12 can be factored and rewritten as 6 times, there's the multiplication, x plus 2. When you hear the word factor, I want you to think multiply. Throughout this unit, we'll be talking about 4 different kinds of factoring. Today, we're going to talk about 2 of them. The first type is called GCF, which stands for greatest common factor. The second type that we're going to talk about today is called difference of squares. A third type of factoring, which we will talk about later in the unit, is called grouping. And the final type of factoring that we're going to cover is going to help us factor trinomials. Okay, so in other words, we want to take problems that are addition or subtraction and rewrite them using multiplication. One or more of these 4 methods will be used. If we cannot take the problem and rewrite it as a multiplication problem, then we call the polynomial a prime polynomial. A prime polynomial is any polynomial that has no other factors besides 1 in itself. And we'll look at a few examples of that today. All right. Let's talk about factoring by greatest common factor. So that's one of the methods that we have for factoring a polynomial. Greatest common factor is the largest number, variable, or both that is common or that is a factor of all the terms in the polynomial. Okay, remember factor means multiply. So I'm looking for the biggest number that I can use to make the terms that I have. I'm looking for the largest variable that could be used to make the terms that I have, or both. Some problems have a greatest common factor that is both a number and a variable. Okay, but whatever we pick has to be a factor of all the terms in the polynomial. So let's look at an example. We want to take something like 6a plus 3b and rewrite that addition problem as a multiplication problem. I need to start by determining the greatest common factor. So the largest number, variable, or both that is a factor of both 6 and 3. So I'm thinking about the largest number that goes into 6 and goes into 3. That number would be 3. If I look at the 2 terms and compare their variables, an a and a b, I see that these terms don't have any variables in common. All right, so my greatest common factor here is 3. Now I want to rewrite this as a multiplication problem. So my factor form is going to look like 3, and then remember we want to rewrite it as multiplication, so 3 times. And then to figure out what goes in here, I'm going to come up and divide both of these things by 3. So 6a divided by 3 gives me 2a, put down my plus sign, and 3b divided by 3 leaves me with just b. This factored form that you see here should remind you of something that we studied earlier in the year, which is the distributive property. I can mentally check that this will multiply to give me this. If I distribute 3 to 2a, that makes 6a. And if I distribute 3 to b, 3 times b is 3b. So I have successfully taken an addition problem and rewritten it as multiplication. 3 times 2a plus b. All right, in our second example, if I'm looking at the two terms that I see there, if I compare the numerical part, 29 and -3, I'm trying to think of the largest number that goes into both of those. Well, the largest number that could go into 3 is 3. And if I think about whether 3 goes into 29, it does not. So these numbers do not share a common factor other than 1. Okay? If I look at the two terms and now look at the variables, what I should see is that this term and this term both share a variable of x. So my greatest common factor for this problem is 1x, or just x. Okay? We now want to take the subtraction problem and rewrite it as a multiplication problem. So for our factored form, it's going to be x times, and then to figure out what goes in the parentheses, I just come up here and divide both of these terms by x. So 29xy divided by x, the x's are going to cancel and leave me with 29y. Put down my minus sign, and 3x divided by x is just going to leave me with 3. So I have successfully taken my subtraction problem and rewritten it as multiplication. X times 29xy minus 3. And if I think about distributing this, x times 29xy makes 29xy, and then x times -3 makes -3x. All right, on the third example, again, we want to look for any numbers or variables that is common or that is a factor of all of the terms in the polynomial. So when I think about the numerical part of each term, 3 and 15, the largest number that goes into both 3 and 15 is the number 3. When I look at the variable parts, I've got x squared, which means x times x, and here I have just a single x. So the largest that they have in common is that they both have one x in common. Okay? So my greatest common factor here is 3x. Again, I'm trying to take that addition problem and rewrite it as multiplication. So my factor form is going to say 3x times, and I need to figure out what I'm going to multiply that by. To do that, I simply come up here and divide each of these terms by 3x. So 3x squared over 3x, the 3's cancel, and our exponent rules tell us that x squared over x to the first is going to make a single x to the first. Over here, 3 goes into 15 5 times, and then the x's cancel out. So I have successfully taken what was an addition problem and rewritten it as multiplication. 3x times x plus 5. And if I distribute the 3x back in, I should get what I started with. Right? On the next three examples, number 4, 3c squared d minus 6c squared d squared. If I'm thinking about the greatest common factor there, all right, so if I look at the numerical part, the largest number that goes into both 3 and 6 is 3. When I look at the variable part, this is c times d. This is c times d times d. So when I look at what they share in common, both of them have two c's that are being multiplied. So they share a c squared. When I look at the d's, what I see is that they share one d in common. So my greatest common factor here is 3c squared d. Right? My factored form, remember, I'm going to rewrite this as multiplication. So my greatest common factor times what would make 3c squared d minus 6c squared d squared. So we just come up here and divide these. And 3c squared d divided by 3c squared d leaves me with 1. Put down my minus sign. And 6c squared d squared divided by 3c squared d gives me 2. C squareds cancel, d. So I have rewritten this as 3c squared d times 1 minus 2d. My next problem has a greatest common, or has a trinomial. So instead of just 2 terms, we have 3 terms. We're still going to do the same thing. Look at the numerical part. What is the largest number that goes into 3, -12, and 15? 3. Look at the variable part. This means I have 3 x's multiplied together. This one means I have 2 x's multiplied together. This one means I have a single x. When I look at the largest that they all share in common, I end up with 1 x that they share in common. So my factored form is going to say 3x times, and then I simply come up here and divide each of these, and I get x squared minus 4x plus 5. So I have rewritten this trinomial as a product. 3x times x squared minus 4x plus 5. Right? On the final one, when I take a look at 3 and 8, there is no number that goes into both of those. When I look at the variables x squared and y squared, there are no variables that are shared by both of these terms. So in this case, the only common factor between 3x squared and 8y squared is the number 1. If I were to rewrite this as 1 times 3x squared plus 8y squared, I really haven't changed the problem. So this is an example where the only factors are 1 and itself. So we call this prime. Okay, meaning that we cannot rewrite this as a product. 3x squared plus 8y squared is the best we can do. Okay, as we continue our conversation on factoring, remember that there were several different types of factoring that we can learn. The first one that we talked about was a greatest common factor. We talk about greatest common factor first because we want to look at every problem to determine if there is a GCF. If there is, great. We're still going to continue through this chart. If there is not, that's fine too. We are still going to continue through this chart. A second type of factoring that we want to talk about today is a binomial, how to factor a binomial. Remember from a previous unit on polynomials that a binomial means that we have 2 terms. Our method for factoring a binomial is going to be called a difference of squares. All right, we'll come back and talk about how to factor trinomials and polynomials another day. Okay. So now we want to talk about factoring difference of squares. Okay, but as we approach any problem, we want to make sure we're approaching it using this organizational chart. Are we looking for this first? And then we can think about, do we have a binomial, a trinomial, or a polynomial left to factor? Okay, for today, after I look for GCF, I want to check for a difference of squares. All right, difference of squares is used to factor. We just said a binomial with perfect squares. Sorry, I had to think about what goes there. That are separated by subtraction. All right, so key indicators for a difference of squares. I'm looking for 2 terms. Both of my terms have to be what we call perfect squares, and they must be subtracted. Okay, they have to be separated by a subtraction sign and only a subtraction sign. What you'll see on the list below is a review of perfect squares. At this point, we should know our perfect squares through 25. All right, so 1 through 20 and then number 25. All right, so we're looking for any of the numbers off of this list to be present in our problem because these are the numbers that are perfect squares. We also talk about variables being perfect squares. And when we talk about variables being perfect squares, an even exponent is going to be considered a perfect square. So something like x to the 6th, we don't normally think of the number 6 as being a perfect square. All right, but in variable world, as long as my exponent is even, then my variable is considered to be a perfect square, okay? All right, the pattern for difference of squares. Remember that we said that we were going to have 2 terms. So for now, we're going to call those A and B. We said that those terms had to be perfect squares, so the pattern is going to be that they are squared. And then we said that they had to be separated by subtraction, okay? So as long as I have something that fits this form, I will always be able to factor it into 2 binomials. So this binomial times that binomial. And the way I do this is I say, okay, in the front, A is what's being squared. So in the front of each of these parentheses, I'm going to write an A. In the back of this problem, B is being squared. So in the back of each of these parentheses, I'm going to write a B. And then in order to multiply and have a negative sign, one of these signs needs to be positive and one of these signs needs to be negative. Right? And it does not matter which order you write it in. You can put the negative sign in the front or the positive sign in the front. You just need one of each sign, but it does not matter which goes where. All right, so let's practice. In the first example, remember our first step is to look for a greatest common factor. Do m squared and negative 81 share a greatest common factor? So is there a number or a variable or both that goes into both of those terms? And the answer is no. All right, the next thing we're supposed to look for, according to our chart, after we check for a GCF, we're supposed to think about whether the problem could be factored as a difference of squares. So if I look at this, does it fit the pattern for a difference of squares? Well, we said we had to have two terms. Those terms had to be squares. Well, m is being squared, and 81 can be found right here on my list, so it's a perfect square. And then we said that we had to have subtraction in the problem, which we do. So this is a prime example of a difference of squares. According to our rule, we will factor it into two parentheses, right? That's the multiplication piece. All right, what's being squared here in the front? An m. What's being squared here in the back to make 81? Well, 81 was 9 squared. So what I'm squaring is 9. 9 times 9 is 81. And then remember, in order to get a subtraction sign, I need one sign to be positive and one sign to be negative. In a second example here, look for a greatest common factor first. I don't have anything in common between 49 and x squared. So I move on. The next thing I'm going to check for is a difference of squares. Right? So do I have a difference? Yes. Of two things? Yes. So there's my binomial. All right. And then do I have perfect squares? Well, 49 is listed right here on the list. And I know that x is a perfect square because it's got an even power. So I'm going to put down my two parentheses. What's being squared here in the front to make 49 is the number 7. What's being squared here in the back to make x squared is an x. X times x makes x squared. And then one of them is going to get an addition sign and one of them is going to get a subtraction sign. Notice I switched up the order of the signs this time just to show you it really does not matter. Okay. All right, next example. Looking for a greatest common factor between 4x squared and 121t squared. Okay, so there are no numbers that 4 and 121 share in common. Also, there are no variables that they share in common. So after looking for a greatest common factor, we are now going to check to see if we have a difference of squares. Difference means subtraction. 2 terms, right? 4 is on the list up here. X has an even power. 121 is on my list right here. T has an even power. So we're going to put down our two parentheses. The number I'm squaring to make 4 is 2. And the number, or what I'm squaring to make x squared, is an x. So in front of each of these parentheses, I'm going to put a 2x. All right, in the back here, the number I square to make 121 is 11. The thing I square to make t squared is a t. So each of these is going to get an 11t, and then I drop in my signs. One parenthesis gets a positive sign, one parenthesis gets a negative sign. Okay. All right, number 4, I checked for a greatest common factor. X squared and 64 don't share anything in common. So I move on and check, is it a difference? Yes. Of 2 things? Yes. Are both of these squares? Yes. Put down my 2 parentheses. What's being squared in the front is an x. What's being squared to make 64 is an 8. One gets a minus and one gets a plus. Again, where I put the plus and minus does not matter. All right, number 5, looking at this, thinking about greatest common factor, 1 and 25 don't share anything in common, okay? And I see this term has an x squared, but this one doesn't have any x's, all right? So there's no variables that these terms share in common. Next, I'm going to check for a difference of squares. All right, remember the word difference means subtraction. Do we have a difference of squares here? The answer is no, all right? So at this point, we cannot factor this at all, and we say that this polynomial is prime, okay? Remember, I can only factor it if that is a minus sign, okay? So don't get tricked there. All right, number 6, looking at the two terms, is there a greatest common factor? No. Moving on, I'm now going to check for a difference of two perfect squares. Okay, so two terms, even power, so that's a perfect square. 49 and 81 are both on the list above. So this is a difference of squares. What's being squared here? Each of these are going to get an X in the front. All right, don't be fooled by the fraction or be scared. All right, 49 is a perfect square, that is 7 squared. 81 is a perfect square, that is 9 squared. So this is just going to be 7 over 9, and then one gets a plus sign and one gets a minus sign. Okay, don't let that fraction freak you out. All right, last 3. If I take a look at number 7, all right, I want to know, is there a greatest common factor there? Yes, there is. 2x squared and negative 32 share the number 2 in common. So my first step here is going to be to factor that 2 out. So take out that GCF, right? 2 goes into 2x squared and leaves me with x squared, and 2 goes into negative 32 and leaves me negative 16. Okay? Sometimes we can do more than one type of factoring. So with what's left over, I now want to check this and see if there's anything else I can do. At this point, the only other thing I know how to factor is a difference of two things that are both squares. So you'll notice that this is an example of a difference of squares, so we need to go one step further. We're going to hang on to our GCF, and now we're going to factor the difference of squares part. What's being squared in the front is an X, what's being squared in the back is a 4, and then we drop in signs. One gets a minus, and then one gets a plus. So guys, this is my final answer because this is completely factored. Leaving the problem as 2 times x squared minus 16 is not completely factored or completely simplified, okay? There was more I could do here, which was my difference of squares. All right, be really careful on number 8. You might be inclined to jump right in and do a difference of squares, but remember the first thing we're supposed to check for is a greatest common factor. So if I think about 100m squared and 25, they do share something in common. They share the number 25, right? So if I take that out, right? 25 times, all right, what's that going to be? 100m squared over 25 is going to give me 4m squared. And then here, put down the minus sign. 25 over 25 makes 1. Right? Remember, sometimes there is more than one type of factoring we can do. So as we look at this is a difference of two things that are both perfect squares. 4 and 1 are both on my list. M has an even power. So I'm going to keep the 25, and I have to break this down further so that it is completely factored. Right? What's being squared here to make 4m squared? 2m. What's being squared here to make the number 1? A 1. 1 gets a minus, 1 gets a plus. So my final answer here is that 25 times 2m minus 1 times 2m plus 1 is completely factored. All right, finally on the last one, I want to check for a greatest common factor. All right, there is nothing in common between 81 and 256. And then I see both terms do not have a p, so they can't share a p in common. All right, thinking about, could this be a difference of squares? Well, I definitely have the difference here. Two terms, 81 and 256 are both on the list above, and p is raised to an even power, so we have a perfect square. All right, write down my 2 parentheses. All right, what's being squared here to make 81 is 9, and what's being squared to make p to the 4th is p to the 2nd. So each of these is going to get a 9p squared in the front. In the back, I have the number 256. So 16 times 16 makes 256. And remember, 1 gets a plus and 1 gets a minus. Not so fast. We're not done. All right. do you notice that anything can be factored further? Well, look at this. This is a plus, so this cannot be factored further. 9p squared plus 16 is going to stay. But this is a difference of squares. Difference of two things. 9 and 16 are both on my list. P is to an even power. So we have to break this down even further. What's being squared here is 3p. What's being squared here is 4, and 1 gets a plus and 1 gets a minus. Right? So you might be asking, well, how do I know when I can stop? Right? Well, when I get down to what we call linear factors, and the reason this is a linear factor is because the power is a 1. When I get down to linear factors, I know that I am probably done factoring. Okay, so 3p plus 4 and 3p minus 4 are linear factors. This is not a linear factor, but again, we already talked about why this could not be simplified because of the plus. So my final answer here is 9p squared plus 16 times 3p plus 4 times 3p minus 4.